Hello friends and welcome at my channel. Today I would like to show you guys 3 examples of the application of the so-called L'Hopital's rule. So let's start with number 1. I hope you're familiar with this rule. Basically it tells you if you have a limit where two functions are, where you have a fraction, for example ln of x dividing by a cotangent of x and x is running towards 0, well, we must admit it runs towards 0 from the positive side, otherwise ln wouldn't be defined. Well, this is the so-called, the cotangent. This is the cosine of x divided over the sine of x. So the cosine is approaching 1 as we are approaching x 0 by x, and the sine is approaching 0 from the positive hand side. So we're dividing by a very small number, so it's getting to plus infinity, and ln is getting to minus infinity. I hope you remember how the graph of it looks like. So this is minus. So basically, this is the case infinity minus infinity divided by infinity, and in those cases we apply the so-called L'Hopital's rule, which is actually not clear where they came from. L'Hopital, most probably it came from one of the geniuses from Bernoulli's family, but this is the way it is. So what we do here, we apply the derivation from both ends for the numerator and for the denominator. We get 1 divided by x in case of numerator. This is the derivative of ln. And what about the derivative of the cotangent? If you remember, cosine divided by sine. So the so-called quotient rule, cosine prime is minus sine, then times sine it's squared, and then minus cosine. So this is cosine and sine is cosine squared as well, divided by sine squared. So minus minus we can take out. It's going to be 1 divided by sine squared of x, of course. So this is what we have here. So minus 1 divided over the sine squared of x. So we can kick minus out. We can produce reciprocals. So basically we have here a limit x towards 0 from the right hand side, minus in front. Because of the factor rule, so sine is coming up. We got sine squared of x divided by x, and well, this is now 0 divided by 0. We could use L'Hopital, but I hope that you know what's happening here, because we have minus limit x towards 0 from the positive side. Let's write it as sine of x divided by x times 1 more sine of x. And I proved it somewhere on my channel previously that this value would be 1. So the speed at which, the pace at which sine of x and x are attempting to get to 0 is the same. So this is 1. And sine, of course, is running towards 0. So all the stuff is becoming 0. This is example number 1. Okay, let's do number 2 now. That would be a limit. X is running towards 0. 1 divided over sine squared of x minus 1 divided by x squared. Well, it's not clearly the case for L'Hopital's rule yet, because this is just something very big minus something very big as well. But we know that x and sine of x are very close to each other at 0. So let's bring it first to the same denominator, see what's happening then. So we have x squared minus sine squared of x here. And now we have x squared times sine squared of x. Well, you see, this is a great case for application of L'Hopital, but the problem is In the denominator, we have a product and also sine squared, which means it's a chain rule and a product rule at the same time. So we'll need to do L'Hopital like many times, maybe 3 times, in order to see something clearly. Let's remember that x is exactly like sine if we are very close to 0. And we are very close to 0. So let's, instead of using sine of squared here, let's maybe substitute by x squared. I'm not changing anything. I can really write equal because I proved previously that those limits are 0 and so on. So x towards 0 here, we still have x squared minus sine squared of x here, but now we are dividing by x to the power of 4. Once again, I am allowed to write 0. Think of this limit and then you'll clearly understand why. So let's apply L'Hopital now. 2x minus 2 sine of x cosine of x divided over 4x cubed. Well, it's getting better because we can rewrite it as a limit x towards 0. We got 2x and now the doubled angle sign, so it's sine of 2x. And here we have 4x cubed. L'Hopital again? Why not? It's 0 divided by 0. So x towards 0 still. We got 2 here. We have minus cosine of 2x times 2. That's all right. Divided over 12x squared. What do we have in the numerator? 0 now. Denominator, 0 again. Let's do it again. But you see, the computation would have become way more complicated if we wouldn't have substituted the sine squared by x squared. So it was crucial. Trust me, I know what I'm talking about. So 2 derived is 0. Cosine giving minus sign, so we got minus minus gives me plus, and then extra 2. So we got 4 sine of 2x here divided over, that's gonna be 24x. And now, well, first of all, we can cancel it. And now let's write it this way. 2 sine x cosine x, 6x. This is 1, this is 1, and this is a third. Isn't that crazy? I think it is. And now the third limit for today's lesson. Let's take limit x towards 0. We've got cosine of 2x and the whole expression to the power of 3 divided over x squared. So what would that be? Well, cosine approaches 0, it's 1. 3 divided by x squared is approaching infinity, plus infinity. So we kind of have 1 to the power of plus infinity. Maybe it's not the best case to apply L'Hopital, but let's change this function slightly to see what's happening. So we consider limit x towards 0 still, but now we'll use a logarithm of this expression, and maybe it will help us a little bit. As you remember, a logarithmical function is a monotonic function, so we are not changing any kind of, especially to the base of e. To the base of a value which is between 0 and 1, we could be changing something, but the logarithm of x in this case is just increasing and we are not changing anything. So let's see, what do we have here? We can apply the logarithmical rules. We are having, I'm putting 3 down, so we are having 3 ln of cosine of 2x divided over x squared now. So what do we have here? We have in the denominator x towards 0, a very small number. So we're running towards 0. What about here? Cosine, it's running towards 1. So it's ln of 1. It's 0 by 0. So now we can apply L'Hopital's rule without any troubles, right? So what do we have? Limit x towards 0 still. Now just a little bit chained function, a little bit more complicated. Ln is 1 divided by x, so we got 3 still. 1 divided by the cosine of 2x, correct? I hope it is. Now the derivative of the cosine would be a minus sine of 2x. And then we have extra 2. And in the denominator it was, I think, only 2x. Yes, okay. Can we simplify something? Well, we can cancel here and there. We can take 3 out, we can take minus out. So we're having minus 3, limit x towards 0. This is a tangent of 2x divided by x. And we proved that the tangent of x divided by x is actually behaving the same as sine of x divided by x, so it's 1. And since we have tangent of 2x, it's just 2. So this is minus 6. All right. Okay, once again, since tan of x divided by x, if x is running towards 0, is 1. I must have done it somewhere on my channel as well. If I'll find it, I'll put a link. Otherwise, just see through my channel. I'm surely have done it. Okay. So what do we know? We know that ln of our expression is equal to minus 6. So our expression itself is just e to the power of minus 6. So that means, by the definition, that we had the limit x towards 0 of the cosine of 2x to the power of 3 divided of x squared is e to the power of minus 6, or 1 divided by e to the power of 6. Isn't that crazy again? I think it is. Because we are dealing with, well, the trigonometrical function of cosine and basically just a hyperbola 3 divided by x squared, and all of a sudden there is an exponential value to the power of minus 6, which is somehow a product of 2 and 3, but with a negative sign. Well, if we know a bit more about complex analysis, then we have more connections between cosine and exponential function. But we're not that far yet. We will be one day. Thanks for watching. See you guys in the next videos.